Good afternoon, everybody. My name is Brian Ashburn. I'm a senior solution architect with Red Hat. As you can see, I have a co-presenter who has not made it here yet. He'll probably be a minute or two late. So I'm a senior solutions architect focusing on our embedded ISV partners as well as customers doing what we classify as intelligent systems, which is really around IoT, primarily on the East Coast as well as Canada. James Kirkland, who will be here any moment now, is the chief architect for IoT and intelligent systems. So the agenda today, because the talk is about IoT protocols, right? I hope everybody ate a really nice big lunch, because we're going to talk about bit twiddling and all those kind of fun things, and everybody can take a nice long nap. Just kidding. So I'm going to talk about what is a protocol. We're going to take a look at some of the common protocols in IoT, where their applications come in, the types of things that you do with them. We're going to talk about protocol implementation. So how do you get access to these protocols? How do you use them? What are some components that provide that? And then towards the end, I'm going to show some things where Fuse fits in. And protocols aren't just one way. It's not just standard. Every industry kind of develops a lot of their own protocols. And so figuring out how to use Fuse to be able to create adapters and things like that to very easily integrate those protocols into your systems. So what are protocols? I mean, it's not just a droid who's going to translate stuff for you that can speak Bocce and all that kind of stuff. But it is a communication protocol. It's a system of rules that allow two things to communicate together. This is pretty important when we start getting into IoT, because most of the things that are talking are two different machines. So they have to agree as to how they're going to talk amongst each other. It's also very important because that's most of what IoT is, right? It's not just one system. You build all of these different components on a single server, and so they're talking together through direct method calls, things like that. Most of this is remote. We're talking about pipelines out in the field. We're talking about trains running down the tracks. All of these things are out there, and we're trying to get the data back so that we can see it, so that we can do something about it. So types of communication in IoT. Machine to machine, right, like Skynet. Yes, that's the Cyberdyne Skynet. Machine to machine communication. This is primarily going to be the devices that are out there talking to other devices. Sometimes those things are going to be things like gateways. So when you have a number of devices out in the field, you don't want them talking directly to your data center based on communication pathways, things like that. So they'll talk to a gateway that will then aggregate that information, maybe perform some processing and send it back. There will be some machine to server. That gateway could be a server. It could be just another very small device. And then you're going to have server to server. This might be from the gateway back to the data center. And then sometimes there's even human to machine communication. Now, I won't be covering any protocols for that because I don't really think there are any. So I mentioned that I'm not going to talk about bit twiddling, but I did put a couple things up here. Just looking whenever you go out and start to look at protocols, the types of things that you're going to use to do the communication, they're going to come in some kind of format, right? So this is an example of some of the MQTT format. It's got a fixed header, so there's 2 bytes in the header. The first one's going to contain the message type as well as any flags. And then the second byte's going to tell you how long the actual message is. There's also the idea of having a variable header, which could not be included. And then, of course, you're going to have a payload, right? This might be application data, or some of the things for MQTT is the connect message, a subscribe message, various things like that. So when you're looking at IoT protocol or looking at protocols, this is the very, very low level of what you're going to see. And a lot of this is going to help you determine what the best protocol is for your particular use case. So lastly, why do we care, right? Why did they give me this slot to come up here and talk to you about protocols? Well, like I said, pretty much all of what we do in IoT is communication. Right? We're trying to get information from sensors back so that we can analyze it and look at it. We're trying to send information down to an actuator to be able to perform some function. We're trying to get that information, people passing through the doors, things like that. When you're going to choose these, there's a number of things that you're going to have to look at in making this choice, right? What are your communication pathways? I know one of the ones that Eurotech was talking about in an earlier talk was about the fact that the only way that they can communicate from the sensors attached to the pipelines is over satellite. So that's a very expensive form of communication, which means that you have to find something that's not going to take a lot of space, right? So using something like STOMP or REST or one of those is just going to be completely out of the ballpark. At the same time, you've got to be able to look at what's the ability, right? What type of things do I need? When you're looking at the server side or different types of routing that are necessary, you might have to have AMQP because you're going to have to need those different type of messaging pathways. And then lastly, it's going to be something like processing power on the device. If you've got a very small, lightweight microcontroller, it can't be doing all of the heavyweight things that are needed for some of the higher level protocols. All right, so now we're going to take a look at some common protocols that we see show up in IoT. The first one is HTTP REST. I've actually seen, which was interesting, some of the people claiming for IoT platforms are completely HTTP REST based, which I found interesting, that any IoT device is actually going to do nothing but talk REST is kind of crazy, but it is out there, right? If you're doing everything on Raspberry Pis, they've got enough power, they can connect to Wi-Fi, you might be able to do everything through REST. It is a very common base of implementation. It's very, well, I'll say HTTP is very well defined. REST, on the other hand, has a good definition, but most people don't actually implement REST. But there are a lot of systems out there that will provide frameworks for either creating REST on the server side as well as REST on the client side. So it's language independent. It doesn't matter if you're writing C, C++, Java, Ruby, Node, whatever. There are going to be REST libraries on both sides of the fence to create and implement the services and the message processing that you need. It does lack many of the features of full messaging systems. So you're not going to get things like guaranteed delivery. If you're doing anything like store and forward, you're going to have to build it on your own. It's not something that's going to be native to the protocol. It's not something the protocol requires the server to implement. And really, I guess one of the big cons I should have put up here is it's pretty heavyweight, right? It takes a lot of data, transferring all of the text, things like that, back to the server. So MQTT, right? This is the one in IoT everybody's heard of, everybody talks about. Very, very common. It is an open standard. It's very lightweight. You can do a whole lot with MQTT with not a lot of bytes, which makes it very, very good for transferring over bandwidth-constrained networks. There's a lot of really good quality of service definitions. So the idea of guaranteed delivery, making sure that something is getting where it needs to go, all of that is defined as part of the protocol. It's not something you'll have to implement yourself. It does define things around a persistent message store. So there's a lot of things to like about MQTT. There are implementations in many, many different languages. The cons are, in the current version, there's only topics, right? So the only thing you can do is publish, subscribe. Now, you can get around that by building topic hierarchies in such a way that Each thing has its own topic that it's only listening to, and that's how you kind of get a point-to-point. But at the end of the day, it's still only topics. One of the other big kind of drawbacks is that when you're sending content over MQTT, that content, the end result reading it has to know what type that is. There's nothing in the MQTT spec that's going to tell you this is a binary format, or this is JSON, or this is XML, or anything like that. Those are not part of the MQTT spec. So you've got to either add stuff in, to kind of piggyback on headers or something like that, or you've got to know what the client is sending and what the server is trying to receive. So there's another one, MQTT-SN, which is about sensor networks. There's a lot of really good things about this in that it's a TCP-less communication, so it's over UDP, which is going to allow you to do things in an even smaller amount of space. You don't have the connection-oriented type of things that we're used to. It was created specifically for sensor networks. And it's got some improvements over the standard MQTT, like an error status. The message header is a lot more concise, so it's taking up a lot less space. So it does have a number of cons, right? One of the big ones being that it is a complex connection mechanism because it is UDP in order to get things like quality of service and various things. Which means that even if you only have 2 sensors on your sensor network talking, you have to set up all of this complex communication framework, right? So it does add a level of complexity in defining it. And even though it is UDP, in order to accomplish a lot of those guaranteed messaging things, it does use stateful endpoints. So it does not define how the broker or client has to react whenever a connection restart happens, right? So if a particular sensor goes away and then comes back, there is no definition in the protocol stating how that connection is going to reestablish, right? What's going to happen to the messages that are there? And a lot of times that becomes pretty important. And it's only supported on a few platforms, right? There's not a very wide array of implementation for it. So CoAP. This is one that's gaining a lot of popularity. It is an open standard. It is implemented using REST over HTTP. But it is extremely lightweight and easy to process. So very good for resource-constrained devices. And this is another one that utilizes UDP. So it's able to do HTTP and REST over UDP, which allows you to get a much more concise message format for the transfer. Now, while it has the ability to observe resources, so to listen on a particular topic, it is not intended for that. It is primarily queue-based, one-to-one connection between one device and another. It is gaining a good deal of popularity. When I talk to customers looking to do IoT, it's one of the things that I'm hearing a lot after MQTT, right? So the first thing is, hey, do you do MQTT? The second question is usually, do you guys support CoAP? So the last one I'll talk about, AMQP, right? This is probably more for server to server, but it is one that shows up a good bit, right? Again, like the majority of these are open protocols. defined based on a community that, a committee that votes for everything. AMQP is a very full-featured message protocol. It has built-in support for routing types. So what I mean by that is, especially those of us that come from the Java world, right? We've used JMS forever. So what do we think about, right? We think about, we have queues, point-to-point. We have topics, publish, subscribe. Well, there's a lot of other ways to route messages besides those two, right? And so AMQP defines a lot of that with things like having the ability to do fan outs, to be able to do different types of filtering and things like that on messages as you're sending them through. The data type encoding is defined in the spec. Now, this goes a little bit above and beyond what I was talking about earlier with MQTT, in that what we're talking about here is not only is there a way to specify the body of the message is a application JSON or some type of type. AMQP defines how the values in the header and what type of data types are usable and how they're encoded, right? So this gives us a very strict standard for how to define what the message header is going to look like, how each of the components in there are going to be written, and how they're going to get transferred over the wire. James and I have actually worked with some standards bodies who have built kind of higher level standards for communication on top of AMQP, and the really nice thing was they didn't have to go through and redefine what all of those data types are and how they were going to be used. They could just piggyback on top of this. And so that's something that's there. It is a heavyweight protocol, so because of those various things, there's usually a good number of bytes that go into an AMQP message. So, you probably don't want to be sending this over radio, right? It's probably going to eat a little bit too much bandwidth. You're going to be able to send a message a minute or something like that. It's not really intended for that. It's intended for you to have at least some type of cellular connection or better. And it's usually better suited for server to server. So a lot of the common architectures that we're seeing as we're talking to customers are they're going to be devices spread out in a particular location. Say in a retail store, there are sensors, proximity sensors, various things like that. All of those messages are going to get routed back to a gateway over MQTT. And then from there, once the data is processed and determined whether or not it needs to stay in that network or go back to the data center, the connection between the gateway and the data center will be AMQP. Because that way it can go back, it can have intermittent hops between there, and things can get routed correctly. That's kind of the common use case that we're seeing right now. Like I said, the CoAP is coming up definitely a lot more. And I'll talk just a little bit about kind of where you can find ways to implement these different protocols. So next, protocol implementations. HTTP REST, I put up here Fuse. I mean, that's one way that you can do it to have it be able to translate into additional protocols. Apache CXF is included within Fuse, so it's a full REST implementation. But REST can really be implemented anywhere, right? There are lots of things in Rails to implement REST. Pretty much every language, Node.js is kind of built up around a lot of REST services and things like that. The benefit of doing something like using Fuse is that it makes it easier to then take those incoming REST communications and translate them into something additional, moving them into AMQP or some other protocol. So MQTT, ActiveMQ implements MQTT as well as MQTT over WebSockets. Definitely a lot of use of that there. When you start to look at the client libraries, pretty much every language almost these days. I don't know. I didn't see a Pascal one. There might be one out there, but there are definitely lots and lots of implementations of the MQTT client. Take a look at the Eclipse Paho project. They've got lots of different implementations there. And we're seeing a lot of people working with, especially things like the iOS client and Android, to get mobile connections back up, right? So if you've got an MQTT broker somewhere, it's very easy to then get those communications. You can build stuff on Android, you can build it on iOS, and connect up and communicate through those networks to kind of add a mobile flavor to the IoT. So CoAP. As far as implementations for CoAP, and I'll preface, right? I work for Red Hat, so pretty much everything that I focus on is going to be towards there. We actually have some work being done by some engineers doing CoAP implementations for Camel, so that we can have a CoAP connector for Camel, both to listen for incoming CoAP messages as well as being able to send them out. So I recommend you take a look at the Camel Labs GitHub site. Find more information about that there. So ActiveMQ was probably the first broker to have a AMQP 1.0 implementation. So it's fully supported there. The AMQP 1.0 clients come from the Cupid Proton project, which provides them in a number of different languages. So there's a Java implementation, there is a C, C++, and a few others that are there. In addition to that, there's the Cupid Dispatch Router, which is still going under a lot of development, but is planned to be included at some point. And that provides peer-to-peer messaging over AMQP 1.0. So that kind of gets away from a lot of the broker, the requirements for the broker, and allows you to communicate directly between clients. All right. I was hoping James would be here by now, because a few of these things he knows a little bit more than me about. So what we'll do is I'll talk about kind of an example protocol implementation, right? So the scenario that I'm looking at here is the business has come to me. They said, hey, we bought this particular sensor device that's going to be sending information back up to us, and it's using this brand new protocol that nobody's got any kind of implementation for, right? Here's the spec for the protocol. It's got a bunch of bytes, for a header. It's got things here. It's going to be talking over TCP on a particular port, right? None of us want to sit down and write a socket server in any language, right? So actually, I'll ask, who here's actually written a socket server running in a production system? Yeah, they're fun, aren't they? Yeah, especially the threading and all of that happy, fun stuff and managing connections. So we don't want to do that. We've definitely decided that. So we want to find a much easier way to do this. At the same time, we've got lots of different systems that this might need to get integrated with, right? Maybe we need to dump it to our big data processing system. Maybe we need to dump it over to some ERP system to notify it about something. Got lots of things that we need to do with it. So what's that going to look like? Well, so this is Camel. Anybody developed on Camel here? A number of you. All right, so Camel is an integration framework that, people call it an ESB, but it's really an integration framework. It provides a number of endpoints and components so that there are lots of things that you can connect to, and then provides implementations of the enterprise integration patterns to do stuff with the data once you get it in. It's very much around a domain-specific language so that it's very readable. So here, and actually I take that back. That sensor we bought is UDP. Sorry. So what we've got is I've created a route in Camel. This is kind of the beginning of the service. We're going to bring data in. I'm going to use a Netty 4 connector. So Netty is a non-blocking implementation of dealing with sockets. So it's very easy to do a lot of scalable, multi-threaded things with Netty. We have a Netty connector for Camel. So using this URI, I'm defining that I'm listening for UDP connections on localhost on this particular port. Now, the data is going to come in, and then I'm going to have to do something with it, right? And it's coming in as some particular byte stream. So that's where I've got this next one, which is a protocol parser, which is just a very simple Java class that I've written with two methods, right? A Marshall method and an unmarshall method. The unmarshall method takes kind of the Camel exchange, which you can get the byte stream from, and it gives you and then what you do is you set that up into an object, and you set that back in for it to be handled through the rest of the route. The other one is to then marshal it, which is going to give you the object that is the current message Camel is dealing with, and then give you a stream to be able to write that down too. So it's a way to be able to read those bytes in that you got on your spec sheet from whatever the sensor was, and bring it into an object that's going to be a lot easier to work with. So next, if we think back to kind of the way MQTT works, marshalling that data, which we did in, one Java class and 5 or 6 lines of XML, we then are going to have to do something, right? Is this a connection request? Is this some type of maybe a store, right? It's telling me, hey, store this sensor information, or maybe it's sending a bad message. So what I've got here is I'm bringing that message in. I'm going to make a choice based on something that got set on that object in the unmarshalling, and then I'm going to send it to a different processor from that. So if we look at that as far as where the route is here, we're taking a look at the body, the thing that we processed, and then we're just making a choice. We're saying, okay, if the message type equals 1, if it equals 2, we can send it over to this different place. So what I'm trying to demonstrate with this is the ease with which you can take something like Camel, which running with ActiveMQ already provides a number of those common protocols, and be able to build extended protocols and extended things on top of it. And that way, as these new protocols start to come around, as these different device manufacturers are building their systems and defining these things, you're able to process that and bring it in and deal with the data that's coming through.